Okay, now we have the impedance data that is well treated. Then we can go back to the main page and we click on the DRT analysis. So again, it is like a blank page, but here what we directly do is I'm going to show you some figures. So again, we load the parameters. We have the same configuration of the windows on the left-hand side, file list, parameters, some buttons, and also the tables. So here we have the compute lambda button, load the parameter, we load the parameters, process the data, and save DRT. I will explain like everything one by one. So first of all, we load the parameter and we process the data. Then we will derive the DRT curve based on the Tikhonov methodology, because here in the method, I tick on the Tikhonov. As everybody knows, we have the critical lambda value to determine how many peaks we can have and what is the extent of the convolution that we will perform with the DRT methodology. So here, what we can do is we can change the lambda. For example, we just make it 10 times smaller, we load the parameter, we process the data, and then we will have more peaks, much more deconvoluted. And if you make it 10 times bigger to 0.005, we load the parameter, we process the data, we can see the peaks are more smoothed. So here, the Tikhonov methodology is performed on the real part plus imaginary part, the real part individually, or the imaginary part individually. All the data will be saved. You can select whatever you want. Theoretically, if the impedance measurement is perfect, you should have these three curves all overlapped completely. Okay, back to the parameters. And then here I also offered the option to compute the lambda. So what you can do is click on the compute lambda button. It will compute the maximum lambda based on the L-curve method. And if you scroll down the parameters, sometimes the screen resolution is not big enough to accommodate all the parameters. You can also see an optimum lambda value, an average lambda value. The optimum lambda value is for the displayed file. That is the best lambda to account for the overfitting or less fitting. The average lambda is the average of the optimal lambda of all 4 selected files. So to have a comparable analysis, we need to keep the same lambda for all the impedance data, which means that once we determine the lambda, it's better to not change it. So what we can do here is that we put the average lambda here, 1.76 or 5. And then we load the parameter, we process the data. And then we will derive like a comparable DRT curves for all the data from EIS01 to 04 in the All tab. And then yeah, we can have already a preliminary comparison. So here, let's go back to the single. Here we have the DRT deconvolution for the data from the KK, smoothed data, corrected data extrapolation, and also the Z-hit, fitted data. And here I also offered a comparison to see what is the fitting result based on the DRT, because KK, Z-hit, DRT, they are all the fitting methodology for the impedance data. So here you can see the points with the truncated original data. You can also see the like a smoothed data based on KK, based on Z-hit, and based on the DRT. We can have also some subtabs to see, okay, what if we want to use KK DRT fitting based on the real part, based on the imaginary part, because in the imaginary part, we does not account for the ohmic resistance. So for the DRT curve, it will start from 0. And you can also see the like a fitting residual of a different methodology. It's all displayed here. That's for the single. And then if you look at the all, as I said, you can already have a comparison to see what is peak distribution of each data. You can also like hide some of them and also unhide of them to have a clear view about the trend of the impedance data that you measured. Now, let's go back to the parameters, because I also offered a lot of different options for the users to check. So we have the minimum lambda, we have the maximum lambda. All these parameters here, it is used to determine the optimum lambda. I do not recommend you to change it unless you are quite familiar with the methodology of L curve and also the like math principle of the DRT Tikhonov deconvolution. But normally it is already enough. The parameter by default, they're already enough to perform the analysis. And here I offered also two options. The first one is optimum lambda, which means that when you click on the process data, the DRT fitting will perform not with the same lambda that we set here. Instead, it will be performed using the optimum lambda of each data. Then this will give you the best peak distribution for most of the time, but it will also put more uncertainty on the analysis of the peak distribution among different files. So normally I don't use this functionality unless necessary. And then here we have the Tikhonov positive. So if you are a frequent user for DRT, for most of the time they never display like the DRT with negative gamma. But here we use like a direct mass inversion, which means that we do not account for the absolute definite DRT. And this is quite useful when we have some negative inductance loop at low frequency. But for the most of the time, what I recommend you to do is to use the Tikhonov positive method. If you click on it, and then if you load the parameter and process the data, it will perform the Tikhonov regularization based on in a positive definite way, and you will have all the peaks, which is like the I would say the most familiar ERT curve that you can see from the literature. What you can do is also to see the peak distribution in the O tab, to see with original data, the KK data, etc., the heat data, the L curve. So on this, if you have a lot of data, you can already have like a quick comparison to see what is the like a peak distribution for all the DRT, for all the impedance data that you measured. Okay. Again, you can change the displayed file, switch between different files, and here I also integrated the methodology from Hong Kong University of Science and Technology, which is I name it as RBF DRT here, using everything is by default. If you are familiar with the DRT tools, you are probably also familiar with functionality here. The lambda, again, if you change it, you change the deconvolution extent. And so now if you load the parameter and you process the data, so this methodology will generally consume more time in Python. I still need to improve a bit the code, but in general, it is usable. But in EPFL, we generally use the Tikhonov methodology. But if you prefer the way how DRT2 treat it, you can also use this method. Okay, so normally it will take a slightly longer while. Okay, the first one is treated, second one, third one, and then you will have the familiar distribution of the peaks here based on the DRT2's methodology for the single file that you displayed here, and also for the like a KK for smooth, corrected, extrapolated, the Z heat, and also you can see how it was fitted based on the DRT that we just performed. And for the O, you can also see the peak distribution and the movement here it's with time. So from 2024, September the 1st, all the way to the 4th. Okay, so now we switch back to the Tikhonov method and we can save DRT. Again, under this folder, the software will create another folder called DRT, and all the data, they will be logged here. The information of the measure, the name file, the file name, the DRT parameters, the Tikhonov based on the real part is in short Tikhonov RE, imaginary part Tikhonov IM, and Tikhonov REIM. And if you have like an extension name called S, then it means the Tikhonov DRT based on the smoothed data from the KK. And then the imaginary, the real part and imaginary part, you have all the like sheets, Excel sheets here, the extrapolated with extension name E, and the CRCT with the corrected, and also the RE based on D, it means the DRT based on the D heat fitted data. And you can also have the RBF based DRT deconvolution, the data. Everything is stored here for the further plot. And most importantly is that the fact that since DRT is also a fitting methodology, it can derive a like ohmic resistance and the polarization resistance based on the fitting, which is much more consistent with the methodology from the KK. If you look at here, if you do a like a screenshot, just for your comparison, let's go back to the EIS. And then if you look at the resistance and also probably the all the data. So here, as you can see, we will expect the ohmic resistance about around like 0.1 or 0.9-ish, but with the resistance fitting based on EIS, it can fluctuate between 0.07 to 0.1. However, for the DRT based ohmic resistance estimation, and it's quite stable from 0.91 to 0.091 and 0.095. So that's why if you want to have a quick idea about the resistances, growth resistance, ohmic resistance, and polarization resistance, you'd better use the DRT DRT fitted resistance estimation for the reference. Okay, that will be all for the DRT methodology.